This is lecture 44. We'll use this pretty purple. It's like lavender for the springtime excitement. A couple things I want to make clear before we start. This is going to be important. What's today? The 30th? Oh man, 30th of April. Okay, so first and foremost, I'm almost done with your final. A couple things I want to say. First off, the final will be uploaded next Wednesday. So that is May 6th. And here's the big important thing. When is it due? You get a week. It's due May 13th. So it's going to be just like the midterm was, take home, open book, open notes. The only rule that I will ask is that you don't talk about it with classmates and that you write up careful solutions. I will post extra credit for those of you who want it. I don't necessarily say you have to do it, but there will be extra credit. Some writing assignments, some math stuff. I don't know. Again, I have no idea what kind of circumstances most of you are under right now. So I'm not expecting anybody to do it, but it's there if you want it. So if you have any questions about that stuff, please contact me. And then the last thing I'll say is I'm working on this now. My goal is to post so I'll post some homework solutions. That way you guys have something. So a couple questions. I mean, I'll pick on Josh. I don't even know if he's on here. Josh and I were just talking. He had questions about homework 9. A few of you have emailed me about past homeworks. Look, my advice when you're studying, particularly this time of year, is do not try to get behind. So what I would be working on if I were you, even if you're missing older homeworks, work on the most current homework. Try understanding that. You can always submit the old homeworks at the end of I don't care. You have until May 13th to submit everything. I don't care when you submit it. As long as you submit it, you will be getting credit for it. Is that clear? I hope it is. Now, that doesn't mean you get a 10 out of 10. Your work's going to matter, the quality of your work, I should say. But I will be happy to accept any homework, any work without a late penalty for it. So hopefully you guys take advantage of that. If there's not an upload button on Canvas for it, email it to me. All right. So, okay. Does anybody have any questions about that kind of stuff? Oh, one thing I will also say is if again, this is a strange time for all of us. If you have issues with resources or technology, if you're worried about how you're going to get me the final or how you're going to find peace and quiet to actually take the final, I get that. You just hit me up, email me. We'll figure something out. All right, enough of that yappity yap. Let's do some friggin' math. So get this out of the way. Get this situated. What do we have here? All right. So last class, we ended with these quote unquote applications of integration. So how I would like to start this class is with the following sort of statement or thought. So what good is integration if we can't actually compute integrals? So what I mean by that is we've talked about this idea of area. We've talked about average value. We've talked about this idea of velocities and accelerations and how integration can be used to help us answer questions. Many of you will learn even many more things that integration is good for. Like perhaps you're in a physics class and you've calculated things like work. Integrals are used to calculate work. They're used to calculate volumes. They're used to calculate lengths of curves. They're used to calculate all types of things that some of you will encounter, not only in calculus, but in other science classes. And frankly, do I sound like an old person now? Frankly, who says that? But frankly, I guess, what good is knowing that you can use integrals to help with that if you don't actually know how to integrate? And what I mean by that is right now, so let me put it this way, good news. Integrals are awesome and super useful. Bad news. We know how to integrate baby functions. That's it. I guess I'm getting ahead of myself. At least so far. So what I want you to understand is that integrals are great, but we don't know how to use them yet. It's like we have a toolbox and we have all these different tools, all kinds of wrenches and hammers and this and that, but we have zero idea how to use them. So what we need to do is we need to go sit down with the experts and figure out how to use each tool. So here's the bottom line. We got to go to the gym and work. We got to do push-ups. We got to bench press. We got to run sprints. We got to squat. We got to figure out how to build up our integration game. So I like to say we need to learn more tricks and methods. That's where we're at today. Okay. Does anybody want to say anything? Just while I take a sip of my chemicals.
How, like, normally how are integrals used in the real life? Like, actual life, how are they used?
What do you mean how in real life? Is that what you asked?
Like, yeah, like how do they help in?
It's endless. We could talk about it until we're blue in the head. I mean, as I mentioned, simple geometric ideas such as areas and volumes are computed using integrals. When you're in physics and engineering, integration is everywhere. Biology, chemistry, probability. You know, we haven't talked about this, but many of you took basic probability and statistics classes before. And you might recall that how you answered questions as you went. You'd look in the back of the book at these tables, these Z tables, or you would go to a calculator and type these things in and you would get a number. Those numbers that you were finding in prob and stats were areas under a curve. And the reason that you kind of looked them up in the back of a book is because they didn't have time to teach you calculus to show you how to get those areas. I mean, look, we could spend a whole day listing applications of integration. It's just one of these things where You know, it's very much, the integral is ubiquitous in science and mathematics, particularly things like engineering. But the unfortunate thing is we don't get to see most of that in Calc 1 or in Calculus 2. We try to point it out, but it's just not something we see. We're basically learning the fundamental tools in a class like this. Hey, there's this thing called the integral. It's important. If you've ever taken a physics class, you probably calculated work on simple problems, like how much work is required to push a box across a desk or something. But imagine a much more complicated question, like how much work is required to split an atom, or how much work is required for an airplane to fly from China to the United States. Those kinds of problems require much more sophisticated tools like integrals. Maybe you've heard of things like flux before, or circulation when you're talking about fluids or chemical reactions. Those things require integration. I mean, we can go on. The integral is extremely, extremely important. Many of you will get to see some of these ideas. Some of you won't. It's just the nature of what it is. So you can really think of an integral, if you want, it's really sort of like a sophisticated sum, because that's what it is. It's a sum. And that means anything that you want to talk about that accumulates, or anything that measures or grows, can be studied through integrals. We now know that the integral is intimately related with the derivative. In fact, they're inverse operations. So that means if you want to study anything that changes, an object in motion, if you want to study the price of a stock, if you want to study the probability or the movement of an electron, or you want to study the voltage of a neuron, anything that changes can be studied through integration. So, I mean, I'm kind of being generic with these answers, but they're not lies. Okay, I hope that, you know, gives you some sort of
Daddy?
Hold on. What, honey? I'm working, honey. What's up?
After you took those princess nail polish, like those princess nail polishes from Grandma O'Grady, where do you put them?
I don't know, honey.
Okay, I just know.
I'd have no idea. You're gonna have to ask Mommy. Does anybody know where the princess nail polish is? No. Okay, cool.
Grandma O'Grady gave them to me last time when we had a pile of toys there. You kept.
Lydia, I'm not trying to be rude. You have to go upstairs, honey. Sweetie, you have to go upstairs.
Okay.
All right. We'll paint your nails later. All right. Okay. Any questions other than where's nail polish? Okay. So, sweet. Oh, by the way, you know, well, we'll get into that soon enough. I don't want to get into that crap right now. So, questions, comments? Okay, so consider the following integral. Now, what we're going to do is we're not going to do a definite integral right now. We're going to do an indefinite one, because we realized that really when you want to calculate integrals, the most important thing is the antiderivative. If your goal is to calculate an integral symbolically or by hand. We'll learn other ways of integrating in the next semester. But right now, the way we integrate is through the fundamental theorem of calculus, which requires antiderivatives. So that means we need to really practice how to get these antiderivatives, or these indefinite integrals, if you will. So let's consider something like this. So if I said to you, how would you compute it? Or calculate. I guess calculate's a weird word here. So what would be some options for how you would determine this? I mean, one of the first tricks we learn as kids when we want to learn something is we guess and check. Do you want to guess and check? I mean, I would say no. That doesn't seem efficient. Do you want to multiply out? I mean, that's one option. I mean, one option is to note that 1 plus 3x quantity squared is 1 plus 6x plus 9x squared. That's one option. So multiplying out in this scenario works. It doesn't require much sort of brain power, provided you've paid attention the last two classes. If you know a little bit of algebra, surely algebra that should be expected of a calculus student, and if you know that algebra and you know how to do simple integration, or as I call them, baby integrals, then it's pretty simple to follow along with, what is this integral? 1 plus 3x quantity squared dx. This becomes 1 plus 6x plus 9x squared dx. And then, of course, now we have three quote-unquote baby pieces to this integral. This becomes x plus 6/2 x squared plus 9/3 x cubed plus our constant. And we can write this in a little simpler terms by simplifying our fractions. So there was nothing wrong with that, and you can even check it by differentiating the answer. If I differentiate the last line, I get 1 plus 6x plus 9x squared, as I expect. But what if I change the problem slightly? What if I said, what about, if that wasn't the second power, what if it was the 10th power? Do you want to multiply that thing out 10 times? I mean, if you wanted to torture yourself, you could. So you could do that. But who would want to? So I hope you see the point I'm trying to make. And that is, in the case where the power is 2, algebra helps you. Multiply it out. In the case where the power is 10, algebra could help you, But that is like essentially dropping an atomic bomb on an ant farm. It's completely unnecessary, provided we have a better way. Yeah. Isn't there other stuff you can use? We got the great nail polish fiasco of 2020. Does anybody have a question though? Comment? Oh, that's what I said. Okay, so the thing we say to ourselves often, at least if we are discoverers, if we're learners, if we want to figure out new things, is there's gots to be a better way. And so one of the things that is a quote unquote trick that we've learned oftentimes before, probably in other classes, but surely in a math class, is if something looks like something else, perhaps we can use our knowledge of something else to gain information about the new thing. So here's an observation. What if we made a substitution? Say, instead of having 1 plus 3x, let's call it a new variable, u. Now, there's some good in this idea, but there's also some bad. And we're going to see why in a second. So the good is as follows. What's good about this? Or what's at least promising? I shouldn't say good. What's promising? Well, we know that the integral of u to the 10th du, we know what this is. This is 1 over 11 u to the power 11 plus c. We know that. So this might help. If we are careful. So what do I mean about being careful? Well, you have to remember that in the original problem, I am integrating, and the variable that we are integrating is x, not u. And so we have to make sure that things aren't sort of being done illegally. We're not cheating. So what do I mean by cheating? Well, here is bad reasoning. We can't just substitute as the integral of 1 plus 3x to the 10th dx equals the integral of u to the 10th du. Because this suggests that dx equals du, which is absurd. Why is it absurd? Well, there's lots of ways for us to think about this, but we gave you a sophisticated way of thinking about it back a few weeks ago, a few classes, when we talked about this idea of what's called a differential. If u and x are related through some formula, then we can create what's called a differential. So what do I mean by that? Well, since u is equal to 1 plus 3x, using differentials, we have u is equal to, excuse me, du is equal to 3 dx. So you might have to go back and think about what we mean by differentials. What we said back in chapter 4 was, if I have a function y equals f of x, we can define a differential, dy equals blah dx. So you might say, where's that 3 coming from? Well, if we come over here and quarter off, one way to think about it intuitively is that if u is 1 plus 3x, du dx, the derivative of u with respect to x, is just 3. And so if you treat this sort of as a fraction, you can reason like this. Now we know du over dx is not a fraction. We know it's the notation for a derivative. However, that is why we adopted this new terminology called a differential. A differential is something that looks like du equals blah or dy equals blah. So what does this suggest? Well, it suggests the following. And again, if you're having a hard time following right now, that is okay. This is some, these are complicated things. But when we do go back to this example, you'll see that I'm trying to explain complicated ideas, because what we're going to do when we compute integrals is we're just going to replace one symbol with another symbol. And then when we do that, you as the student, you as the learner, you get in the habit of just thinking that that's all we're doing, that we're just replacing something with something else. But what I'm asking you to do is think about why we're doing this replacement, why it is logically sound. That's what I'm asking you to do. Challenge yourself to understand why, not just manipulate symbols. Okay, so if we think that this is reasoning is better reasoning, what we have is the following. So this suggests that the integral of the quantity 1 plus 3x to the power 10, what this suggests is, if we substitute not just the variable but also the differential, that this becomes u to the 10th, and it's not dx, it's what? Well, if you go to the previous page, what was dx equal to? Dx is 1/3 du. Which of course we know is 1/3. The integral of u to the 10th du. And now our u, which is the variable, matches the differential du, which means our formulas for this now are valid. This becomes 1 over 11 u to the 11th plus c. And then if we do some cleaning up and we take out u and put the original variable in, we get this. So if you have a question about any step, please ask. We're going to explain what this means in a second. So if you have a question, now's a good time to say, what has happened? Anybody on the chat line, on the voice line, on the it's going to be May tomorrow line? I don't know. Someone, there it is. It's blinking. I love when I get the more blinking. Chat, what is the question? There it is. Fink, this is the greatest question. You guys are always worried about the final answer. Yes, that is the correct answer to answer your question. That is correct, but how do we know it's correct? Well, let's answer that. Well, is it correct? Well, the easy answer is yes. And you can check. By differentiating. I mean, look, take the derivative of what you got. Take the very last line. Take the derivative. You bring down the 11. What's 11 over 33? It's a third. Recopy what's inside. So let's do it. Let's check. We'll come up here and we'll do the check. Because why the heck not? We'll use this pink. This nice spring color, according to stereotypes. So let's take the derivative of this. I'm not going to write the plus c part because we don't need it. What's this derivative? It's 11 over 33. Recopy what's inside. And then by the chain rule, it's times the derivative of what's inside, which is 3. And so the 11 over 33 is 1/3. You multiply that by 3, you get 1. So this simplifies to what we started with. And we celebrate. Now, we showed that it worked in one case. Does this mean this always works? Well, the answer is no, it doesn't always work. It worked here. Does anybody have a question before we elaborate more on what I'm talking about? Off the clap or something, stretch. I should shave. Amy told me I look like an old man. I got gray beards. Too bad, like, now that these are like YouTube, I think like 3 people have seen these videos. I can get Rockstar to pay me because I'm like promoting their chemicals. This would be good. I'm going to start tagging Rockstar in my YouTube videos. Okay, no questions. Good. So it worked in that case, so we might ask, does this always work? So does introducing a new variable, like we did above, we went from x to u, so does it always work? And the answer is no. But it often does. And that's why we study it. And also, we need to know why it works. We can't just say because it worked once. And we can't, I mean, I guess we can argue since we checked our answer that it's correct. But what we want to do is we want to know why it's really working, what's happening. And the key observation to make is that what we did is we actually had, the original function was a composition. And if you remember when we did our check, what derivative rule did we do to check it? Well, the derivative rule we used to check was the chain rule. And then we start getting our cobwebs in our brain away, and we start thinking, we start using our brains and the muscles up there, and we get the neurons firing, and we start thinking, oh shit, that's right. The derivative is connected with the integral. They are inverses. So that would suggest that all the derivative rules I have corresponding statements in terms of integrals. I repeat, since integrating is the reversing of the derivative, we would expect that all of our derivative rules, like the product rule and the chain rule, should have some way of expressing that rule, or we should have a way of expressing that rule in terms of the integral. So let's see that to be true, and let's see why. So if it often does, the question would be when and why. I like this. I'm having fun. How many people have joined us today? There's 12 of you. That's not even half of this class. And as Amy just said, is anybody even awake? She hears nothing. It's like everybody logs in and takes a nap, except Fink, who asked the question. Very good.
I'm awake.
I'm kidding. You know this, Shobit. You know I'm teasing. Ah, Zach. Thank you. Well, I can't wait. By the way, that reminds me, I really hope you guys use those. You know how they email you those teaching evaluations? I'm going to ask you guys questions on the final about some things. I would really hope you do those teaching evaluations and be honest, because who knows what's going to happen the next semester or so with how classes and campus, who the heck knows what's going to happen going forward. I'm really interested in your opinions on how you think any of this went, good or bad. And one of the things I'm curious is it worth my time doing what we're doing now? I don't know. So hopefully you guys will be honest and answer those questions. It would mean a lot to me as someone who hates sitting in this chair doing this. I need to be in a classroom screaming and yelling and making insults. You know how I roll. All right, so let's think about why this is true. And along these lines, it will give us a systematic way of doing certain integrals. So the previous problem especially our check suggests something. What does it suggest? This is an O, not a D. Suggests that the chain rule is causing, or not causing, that's a very poor choice of English. So the chain rule is behind what happened. And let's see why. Dun, 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 dun. Okay, so here's what we want to do. Let's write the chain rule out. So let's recall the chain rule. What does it say? It says if you're going to differentiate the composition. So let's write it like this. So I'm going to take F. We'll use a different color. I'll use pink. And we composed F with G. And we want to differentiate this creature. One way that we could write this, one correct way of writing this derivative is you take the derivative of the outside, F prime, evaluate it at the inside, times the derivative of the inside. So the derivative would be, this is what we used on the previous check. You take the derivative of F, and then you plug G into it, and then you multiply by the derivative of G prime. That's the chain rule. Woo. Okay, so let's assume some things now. Oh yes, Michelle, you want me to go back? Okay, cool. This slide, let me know when you're ready. No problem. You don't have to apologize. That's what we're here for. Okay, so that's the derivative of, or excuse me, that's the derivative of a composition, and the name for this rule that we've adopted is called the chain rule. So what we want to do now is we want to try to rewrite this thing not in terms of derivatives, that d dx. We don't want to write it like that. We want to write this in terms of an integral. So let's think of the metaphor or the analogy or whatever the heck. You know, so Michelle, since you last talked, I'm assuming you're younger than me. And I could state a fact that Michelle is younger than Ryan. That is a fact. Now, you could also say that same fact as Ryan is older than Michelle. So those are two English sentences that describe the same fact. Now, right here on this whiteboard, I have a fact about F and G, and it's written in terms of the English sentence that uses derivatives. What I'd like to do now is I would like to take this sentence, and instead of writing it in terms of derivatives, I want to write it in terms of integrals. So how do I do that? Well, we're going to do it, and we're first going to make an assumption because it's going to help us. So assume F is the derivative of someone else. Let's say big F. So what does that mean? That means big F prime is equal to little f. So let's rewrite the chain rule. So I'm going to rewrite it for a special function. I'm going to rewrite it for f, capital F of g. So let's go and do this slowly but surely. So I take the derivative of capital F, not lowercase f, and I'm going to evaluate it at little g. So I'll get my pink out because that's nice. I love these colors. This is nice. So the chain rule says you take the derivative of the outside. So that's capital F prime, evaluated at the inside times the derivative of the inside. So we get capital F prime evaluated at g times g prime. Now, of course, we assumed that f prime was some function, which we're going to call little f. So this simplifies under this scenario to little f of g times g prime. Okay, so what does this mean? Well, let's think about the language. The language says one of these guys is an antiderivative of the other guy. More specifically, it says capital F of g is an antiderivative of little f of g times g prime. So another way of saying that is if you integrate both sides, if I integrate the left-hand side, it kills the derivative. That's the fundamental theorem of calculus. So what you're left with is you're left with f. If I integrate both sides, I'm left with f evaluated at g of x, capital F that is, plus c is equal to the integral of little f of g of x times g prime of x dx. So I have now written the same fact in two different sentences. One sentence uses derivatives, the other sentence uses integrals. Now, if I know this, and by the way, it should be, let me be very clear. This is overwhelming to look at this green sentence and the black sentence and the blue. All these symbols are overwhelming and scary. I get it. But if you want to understand why what you're going to learn, this symbolic manipulation you're going to do over and over again, if you want to know why it's true, this is why. Because what we just did is we showed it's true for generic functions, f and g. We assumed nothing about f and g, only that little f was the derivative of big F. So we can even make this look prettier if we'd like. So what we do is we summarize as a theorem. This is called the change of variable theorem. Or most books call it the u-sub theorem, u-substitution. So if u equals g of x, and f is continuous, then a complicated integral can often be reduced to a simpler one when the integrals make sense. So that just means you can actually take an integral. Now, am I asking you to memorize this? No, don't memorize it. We are stating a logical reason why it's going to work. What you're going to need to do is know how to use it. So I use this little metaphor or analogy all the time. You don't drive down the road with your driver's manual in your lap, and everything you see, you go and refer to the manual. You don't do that. And learning calculus and learning anything for that matter is no different. You want to practice and do examples and gain repetition with things, and that's how you learn them. You don't memorize things. And I was screaming at the class earlier today. I find it so amazing, and some of you might do this, and I apologize if I offend you, but like memorizing things with flashcards seems like the most ridiculous thing to me. Like, you need to learn by doing. You need to learn by experiencing. You don't learn by just memorizing symbols, at least in my opinion. Okay, so the way I would encourage you to think about this, and please interrupt me if you have a question or a comment. The way I would like you to think about this is as follows. Here's the key idea. A u sub might make unknown integral equal to easy one. Okay, thank you. I'm glad you found it. Oh boy, hold on. Ricky, what are you going to show me? Come here, hurry up.
It's a toy.
It's a toy? Ooh, did you get your nails done too?
It's her first time.
It's her first time? Let me see. Let me see. How pretty. Ooh, beautiful.
She has two colors, and
But your shoes are on the wrong feet, Ricky.
Actually, I have rainbow.
I understand that.
All right, Ricky, we gotta switch.
All right, girls, have fun.
I
Bye. Okay, thank
Ricky,
you.
I gotta
Bye.
switch your shoes.
Have fun. Go fast. All right. Any questions? See how this is perfect. They act up. I give you time to ask questions. So again, do not try to memorize this. I mean, you can if you want, but I'm not suggesting it. What I'm suggesting is you do examples until you see that there's some pattern. The nice thing about that I will say about this, if you do take the time to learn this formula that you see in the middle of the screen, is that it shows you what types of integrals are candidates for a substitution. And a good sort of generic rule of thumb is if you see grouping symbols, it's likely a candidate for substitution. So let's do some examples. And again, if at any moment you have a question, you have to sort of give me the slow down, O'Grady. So the first one we will do is let's do the square root of 8x plus 6 dx. So the way I would encourage you to think about it is I am asking you to integrate the composition of two functions. When I look at that integral, I see grouping symbols. And the grouping symbols is the square root. And that square root or those grouping symbols scream to me, they say, okay, I got something inside of something else. And so that is a good candidate for a u-sub. So let's maybe write these out like this. What is this equal to? So the grouping symbols suggest that I set u equal to 8x plus 6. Now, if u is equal to 8x plus 6, then I know that the derivative of u with respect to x is just 8. Which if I write in differential notation tells me that 1/8 du is equal to dx. So this is a line of reasoning that I want you to become comfortable with. You choose a new variable, and then you compute its derivative with respect to the old variable. Here, my new variable's u, my old variable's x. And now, once I know how u and x are related, what I'd like to know is how du and dx are related. And the way I can sort of show that is by using these differentials. And so what does this tell us? Well, the theorem then tells us that the integral of the square root of 8x plus 6 dx, this becomes the integral of the square root of u times 1/8 du, which is 1/8 times the integral of the square root of u, which I'll write as u to the 1/2. When I integrate that, that becomes u to the 3/2 over 3/2, which is 2/3 when you multiply. And so the very last thing you have to do is you have to go and write things in terms of the original variable. So this is 1/12 times 8x plus 6 to the 3/2 plus the arbitrary constant. So take a moment to think about any questions you might have. Now, I got to be honest with you. Some of you may have seen this before. Some people, when they teach this substitution theorem, they teach it differently. They teach you how to compute these differently. This is how I like to teach it because I think this is the best way of learning it. That's my opinion. If you've seen a different way of doing these, as long as it's correct, I don't care if you use it. That's cool with me. If you go on YouTube and watch videos or look at examples in books and online, you might see how these are reasoned slightly different. I am giving you my method, how I like to reason them. Does anybody have a question? All right, let's do another one. change colors here. So how about we integrate 1 over 1 plus 36x squared. Okay, so what's my thought process here? My thought process is I see grouping, and so that made me, you know, you might say, how do you see grouping? Well, I do see grouping. I see something divided by something else. That's grouping. And so since you see grouping here, that you might say, well, maybe I'll let the denominator be u. Turns out that won't work. And what I would encourage you to do is try it and see why. So
Is it because it will become 0 on top when you do minus?
is it because of what? I didn't understand your question.
If you put u, yeah, it will become 1 over u. And when you try to make u like a number itself without a fraction, it will become u power minus 1.
Well, no,
And when
that's
you try
okay.
to
That's not the issue. The problem is if you try to set u, if you try to do this, let's just show you what happens. Well, if I set u equals to 1 plus 36x squared, that implies that du is 72x. So du dx is that. This is a good example of how not to use the substitution rule. So if I do this and I solve for dx, what is my dx? My dx is 1 over 72 times x du. So what you'll see here is you went from bad to worse. What do I mean by that? Well, you went from one thing you couldn't integrate to something that doesn't make any sense, because now if you plug in, you get 1 over u times 1 over 72x du. Well, now I have two variables. It's not even defined. If you know, being that there's a u and an x in there, that we don't know it, there's no definition for that.
So when you're using substitution and then when you find dx equals to something du, there should be no x over there, right?
Well,
That's
no,
what you
there
mean.
could be an x, but it has to have something. And we'll see examples in a second. There can be an x in your d. That x can be there, but it has to have something that removes it in another part. It
Okay.
has to. A very cheap way of saying that is it has to cancel out somewhere, and it didn't cancel out here. So you went. So basically, you're trying to integrate, and you have two variables inside. That doesn't make sense right now. It's absurd. It's not defined. Now, there are times where you'll get an x and you'll get dx equals something with x du. That can be okay. We'll see an example of that next. So what's the correct reasoning? The correct reasoning is to think about what the original integral looks like. If you have a good sort of understanding of your derivatives, you might say to yourself, hey, that integral we're after almost looks like the integral that would be the arctan. So correct reasoning is to recognize that 1 over 1 plus 36x squared is the same as 1 over 1 plus 6x quantity squared, and set u equal to 6x. This is the correct reasoning. And then when I set u equal to 6x, I obtain du dx equals 6, which of course you can write as dx equals 1/6 du. And so if you make this observation and you apply the theorem correctly, this integral becomes this with a 1/6 out front. And this is just 1/6 the arctan of u. And if we plug back in our original variable, we obtain this, which we can verify as correct through differentiating.
So you found arctan because it's an integral of 1 over 1 plus u squared, right?
That's correct, because in my head and through my practice, I know what this integral is. This integral that I'm hovering the pen around, this should be embedded in your brain for the final, and it should be embedded in your life anytime you take a math class the rest of your life. This is a very important integral. It will show up many, many times. Questions, comments? Okay, so let's look at another example. And I'm choosing these examples on purpose because I want you to study them and see the subtle differences. So the next one we're going to do this one is going to look almost identical to the one we just did, only now it has an x upstairs. So here, u equals 1 plus 36x squared will work. Let's see why. And this goes to your point, Shobit. If that is the case, if I choose that to be my new variable, then when I differentiate, I get 72x. And of course, if I rewrite it in differentials, I can write dx as 1 over 72x dx, excuse me, du. And so here's a way to think about what happens and why we don't get an absurdity. Because our original integral, which is this, when we put our substitution in, let's reason it like this. I got x over, this just becomes u, and then this is times 1 over 72x dx. And if we just sort of think about what happens here, these x's cancel out. They're not really there. And so if we pull the 1 over 72 out, this is 1 over 72, the integral of 1 over u du, which becomes 1 over 72 log of u. And if we replace our original variable back, you get this, which is kind of sloppy. I feel bad. I'm like squishing it in there. Let's see if we can make this look prettier. I apologize for the ugliness, which I guess is in the eye of the beholder. So one question you might say, though, is what would happen to the absolute values? And I would tell you, you don't need them because it's a positive number for all x. So if you have a question.
Is there a way where you can substitute both variables? Like, is there any?
Is there a way where what?
So you substitute the downer equation and also the top one, but it's never possible.
I'm not quite sure what you mean. Say that.
Like x over 1 plus 36x squared. So you replace x, like you substitute x, and you also substitute the downer equation.
Well, I mean, if you do it correctly, I mean, if you wanted to rewrite that x in terms of u and do that, you could. It would cancel out as well in this particular problem. I mean, look, this is going to be something you're going to learn real quickly, that every integral, in a way, is sort of its own entity. Integration turns out to be much more difficult than taking derivatives. And it's just the way it is. So with this strategy, why did it work here? It worked here because the denominator was degree 1 more than the numerator. If I gave you this problem with an x squared upstairs, substitution would not work. So there's lots of subtleties that we could give you that are going to, you know, I'm trying to think of a good way to explain this. So, you know, if an integral that's done by substitution and it works like this, if we just modified one of the pieces, if we just switched it or added something, it's not guaranteed to work using this strategy. So it's kind of hard for you to, I have to sneeze, hold on. I think I have to sneeze. Excuse me. So it's hard for you to appreciate that right now, but let's sort of try to illustrate what I mean through a couple, you know, I'm not going to go through them because we got to end, but let's call this food for thought. So the previous strategy wouldn't work on, say, x squared over 1 plus 36x squared dx. Or the integral of x plus 1 over 1 plus 36x squared dx, etc. So the only way that you're going to have an appreciation for what I'm trying, the point that I'm trying to make, is that if you just open up a book and do lots of examples. That's really it. The more experience you have, the easier that these themes come to you. It really is, if anything, integration is literally nothing more It's a skill that you just can't memorize. It's not a procedure. It's not an algorithm the same way that differentiating is. It requires skills. Now, that being said, we've got sophisticated software that can integrate very easily too. But your job in this class is to show that you can do certain integrals as well. All right, does anybody have a question? Okay, if you guys don't have questions, I say I will see you tomorrow, unless something comes up. And I will stop recording now, and I will post an assignment later. So if you have any questions, hit up my email. Take care, everybody.